We shall now talk about a few more binary operators, namely the logical operators and the bitwise operators. We shall be discussing three logical operators. This is called the logical AND, this is called the logical OR, and this is the logical NOT operator. In order to understand their working, let's take an example. If we say x is 10 and y is equal to 20, and I use the condition x less than 11 and y less than 21. 10 is less than 11 is true. 20 is less than 21, this is true. Since both the parts are true, the result happens to be true. And means all the parts should be true. Or means any one part can be true. Now take a look at it. X is less than 11. This is true. 10 is less than 11 is true. X is less than 21 is also true. So here both are true. So this happens to be true. So the minute one part is true, it will not even go to this part to check it, because OR means if any part is true, the complete thing is assumed to be true. So what it means is true if one of the statements is true. Okay, in order to understand OR, I can also give you another example. Let us say I write like this. I say x greater than 11 or y less than 22. This is false because x is 10. 10 is greater than 11 is false, but still this entire statement is true because 20 is less than 22. The OR indicates one of them must be true. False ORed with this part happens to be true. So either one of them must be true. So since this part is true, we treat it as true. Now let's take a look at what is NOT. NOT means it reverses whatever is the result. Now take a look at this. X is 10. 10 is less than 22 is true. And X is 10. 10 is less than 30 is true. So this part is true. Anything after the AND is also true. But outside the bracket, I am having the NOT. This whatever is within the bracket is true. But the NOT reverses true to false and reverses false to true. NOT is like an inverter. It changes from true to false and false to true. AND means all must be true. OR means any must be true. NOT means reverse the result of the operation. If it is true, make it false. If it is false, make it true. Now let us understand bitwise operators. You know that in computers, everything is stored in terms of zeros and ones. So we can manipulate at the level of an individual bit. Okay, we can manipulate at the level of an individual bit in a computer. So here what I am doing here is I am representing two numbers x and y in bits. So this is the operator. This is the bitwise AND, bitwise OR, bitwise exclusive OR. This is left shift, this is right shift, and this is the bitwise complement operator. Let us say x is equal to 21 in decimal, which is represented like this. Y is equal to 92 in decimal and it is represented like this. Now if I do x and y, see what happens. AND means both the bits, if they are 1, only it is 1. This is 1, this is 0, this is 1. 1 and 1 is 1. 1 and 0 is 0. 1 and 1 is 1. 0. 1 and 0 is 0. 0 and 0 is 0. AND means both should be 1, then only it is 1. Otherwise it happens to be 0. Now let's take as bitwise or inclusive OR. OR means any of them one should be 1. So in this case, either of them is 1, this is 0, this is 1, either of them is 1, this is 1, 0, either of them is 1, this is this thing. This is the symbol for OR, okay, don't confuse it with 1. So this is the result of X bitwise inclusive OR. This is the result of X bitwise AND operator. AND means both the positions should be 1, OR means either of the positions should be 1. Exclusive OR, this is a little almost similar to OR, except that it has one difference. If both are zeros or both are ones, the result is a zero. So take a look at it. So 1 and 1 is not 1 in exclusive OR, it is 0. 0 and 0 is always 0. 1 and 1 is again 0. 1 and 0 is 1. 1 and 1 is 0. This is 0. This is 1 and this is 0. So if you look at it, this is matching it with in exclusive OR. If you take a look at it, it is going to be 0 1 0 0. This also should have been, oh, this last one is 0. I have made it 1. That's why I'm getting a different answer. This is not 92. It's a different number, but doesn't matter. The concept is important. Okay, this is not 91. This is probably 93. Okay, because it's not even yeah, it's not 93 also. It's something totally different. It's a different number. So don't worry about this decimal number. But the idea here is when you do a bitwise exclusive OR, 1 and 1 is 0, 0 and 0 is 0, except if both of them are different, then only you have the number as 1. So this is the answer of exclusive OR. Okay, this is correct when you look at this particular fellow. This is okay. This number is different. It's not 92, it's some other number, but doesn't really matter. Now left shift. Suppose this is a number 21. I am left shifting it by 2 bits to the left shift by 2 positions. So what happens is this 1 and 0 are shifted to this side. So what happens is these 2 zeros are lost. Left shift means these leftmost 2 zeros are lost. Shifting by left to even 1 bit is equivalent to multiplying by 2. Since I'm shifting it by 2 positions, 21 into 2 is 42. 42 into 2 happens to be 84. Left shift by 1 bit is equivalent to multiplying by 2. Right shift by 1 bit is equivalent to dividing by 2. So when I shift 100 by 2 bits to the right, okay, it is as good as dividing by 4 because 2 raised to 2 is 4. 100, when I shift it by 1 bit, it becomes 50. Since I'm shifting it 2 times, it becomes 25. If 100, I had done a left shift 2, it would have become 400. 100 becomes 200. 200 again multiplies by 2, it becomes 400. The moral of the story is left shift by 1 bit or 1 position is equivalent to multiplying by 2. Right shift is equivalent by dividing by 2. You can only do left shift and right shift on numbers which do not have sign positive and negative, which do not have a negative sign. If you have a negative sign, then the behavior is going to be undefined or unpredictable. Bitwise not. Bitwise means ones become zeros and zeros become ones. So if you look at my X, it is 0001 01 01. So here this 0 has become 1, this 0 has become 1, this 0 has become 1, this 1 has become 0. Okay, and the next 0 has become 1, 1 has become 0, 0 has become 1, and finally this is 0. So when you are doing bitwise not or bitwise complement, zeros become 1 and 1 becomes zeros. Now let's take a look at the other shorthand assignment operators. This also I'll need to give you some examples to have clarity. Now suppose I have numbers like this. Okay, let's put some paper so that it doesn't okay, let's take something like this. Let's say x is equal to 10, y is equal to 20. If I say x is equal to y or x is assigned the y, x also becomes 20, y is also 20. Now there are something called as shortcut operators in C. For almost all of these operators you can do it in a shortcut fashion. So I can say x, okay, if I do x plus assign the value of y, this is as good as saying x is equal to x plus y. What was the old value of x? It was 10. What was the value of y? 20. So x becomes equal to 30. So this is known as a shortcut assignment operator. You have this shortcut for this, you have it for multiplication, you have it for subtraction, you have it for division, you have it for modulus, you have it for logical and, logical or, bitwise and, bitwise or, and so on. But okay, you have it for division. Here you can see modulus, bitwise and, bitwise or, logical, bitwise XOR, left shift, right shift, and so on. These are all shortcut assignment operators. What it means to tell you is, if I am doing like this, x is equal to x minus y. So okay, so let's make x 100 now. Let us say x is 100 and y is 25. So this is equal to 100 minus 25. So x is now equal to 75. This is the normal way I do it, but I can also do it like this, x minus equal to y. This internally gets converted to, x is assigned the value x minus y, and the result is also going to be 75. This is easier to understand, this is difficult to understand. So the moral of the story is, please avoid, or better avoid, these shortcut assignment operators, because they make your code a little more difficult and harder to read. All right.